So we're going to solve this system of three equations, three unknowns. We may need to use a calculator just to get some of the computations down. So if you remember, Primère's rule involves us taking determinants. Where we introduced the idea of a determinant last time. We're going to need to take determinants of four different matrices here. We're going to have a D determinant, a dx determinant, a dy determinant, and now because we have three variables, we're also going to need a dz determinant. So it will likely take us the whole screen just to calculate each of these determinants. But you know what? We're going to do it mostly by hand and use a calculator for little spot calculations here and there. And I think it's going to be a lot of fun. I hope you agree with me on that. So let's try it out. The D determinant we'll just erase that. The D determinant is going to be the determinant of the matrix where you just take the coefficients of everything to the left of the equal signs. So 9, -1, because if that's minus y, it's really -1 is the coefficient. 2 from 2z, 3, 9, -1, 1, 2, 9. And once again, as you can see, there's not going to be any shortcuts here. We'd love to expand along a row or a column that had some zeros in it. But from what we can see here, there's nothing. There's no zeros anywhere in this matrix. So again, there's no shortcuts in this one. This one's just going to be a good old-fashioned fun time that we're going to have. So let's maybe use a different color here, kind of spice things up on the screen. So what we're going to do is we're going to expand along, well, if there's no shortcuts, let's just expand along the first column. That's going to be kind of the usual procedure. So that's going to be equal to, we take the 9, and then remember we delete the row and column temporarily that the 9 is in, and for this leftover little thing here, we take the determinant of that. So we do 9 times the determinant of that little 2 by 2 matrix that's left. Then we do subtraction. Then we come down here and we expand along the 3 here. We delete the row and column that the 3 is in. The 3 is going to be here. Then we multiply by the determinant of the leftover 2 by 2 matrix. So -3 times the determinant of -1, 2, 2, and 9. Then it's plus. Then we expand along this 1 here. So it's +1 times the determinant of this leftover business. And we're going to work this whole problem, and it's going to be quite a bit of little mini calculations that we have to do. And there's just no avoiding that, unfortunately. And so now this is going to become 9 times. Now remember, to do a 2 by 2 determinant, you multiply along this diagonal, then you subtract the product of this diagonal. So it's 9 times 9 minus -1 times 2 minus 3 times -1 times 9 minus 2 times 2 plus 1 times -1 times -1 minus 2 times 9. And so we're just going to have to be pretty sharp with little mini calculations here and there. That's going to be 9 times 81 plus 2. If you think about it, minus 3 times, well, -9 minus 4 plus 1 times, since it's just 1, we don't need it, +1 minus 18. And now I'm going to give myself a little more space. And again, like I said, the numbers, if you were to see a problem like this on the final, the numbers aren't going to be quite this large. You're going to be dealing with much simpler calculations. You're going to have 747 plus 39 minus 17. You're going to end up with 769. So again, yes, I am using a calculator in order to do some of these calculations. What I'm also going to do, in order to be very darn sure that I have the right answer, I'm going to double check something. And yes, 769. So I'm just going to kind of write them along the top here, what each of them are. D is going to be equal to 769. And now I have the blessed joy of deleting all this. Now we need to compute each of the individual D matrices for each of the variables. So we need to compute dx, which is going to be the determinant of, it's going to be a 3 by 3 matrix again, only this time we replace the entire first column with the solutions, -26, 34, and 80. And they're called the solutions. That's kind of a bad word for them because they're not the actual solutions we're looking for. But at any rate, we're going to have -26, 34, that's bad, 34 and 80. But then the second and third row, or excuse me, column, are the same as what they were previously. So -1, 2, 9, -1, 2, and 9. So we're replacing the first column because we're solving for the first variable in alphabetical order here. So it's pretty logical, it makes sense. So we're going to have -26 times a 2 by 2 determinant. And maybe you can see it. Maybe I'll help you out here, but I won't be able to do this forever and always. We're going to be left at that 9, 9, -1, 2 thing. -26. And then it's minus 34 times the determinant of the leftover 2 by 2 matrix whenever we cross out the row and column that 34 is in. So it's going to be the 2 by 2 determinant -1, 2, 2, 9. And then it'll be plus 80 times the determinant. Now imagine I crossed out the row and column that the 80's in. -1, 2, 9, -1. And now I'm slowly but surely going to make my way down the line calculations wise. And you may remember that ended up being 81 plus 2, which was 83. And yeah, I need a calculator. The numbers are just going to get too large, which again will not be a problem on the final exam. But this is still an interesting one to work. Minus 34 times, this ended up being -9 minus 4, which was -13. So we'll kind of skip to the good stuff here. Plus 80 times +1 minus 18 ended up being -17. And these numbers are going to be quite a bit ridiculous. -2158 plus 34 times 13, 442, minus, because that's 80 times -17, minus 1,300, excuse me, and 60. And all told, you're going to end up with -3,076. And again, for the safety of what we're doing, so we don't get wrapped up in anything, I'm going to double check this. -3,076. Very good. So this is going to be our dx matrix. And by that I mean determinant, because it's just a single number. It's not a whole matrix. -3,076. So we kind of sigh. What I'm going to do is I'm going to do something clever here to save myself a little bit of grief. So now this time, we need to take the entire second column and replace it with this solutions column here. And now we're computing dy. And I'll use a slightly different color. So now the second column gets replaced, and the first column needs to be this 9, 3, 1 business. Imagine taking our D determinant and just replacing the second column now, but leaving the rest of it the same. And now we can perform our determinant calculation here. We'll expand along this first column. So you're going to have 9 times the determinant. Now erase the row and column the 9 is in. It's going to be 34, negative 1, 89, minus 3 times the determinant, negative 26, 2, 80, and 9, plus 1 times the determinant, negative 26, 2, 34, negative 1. So 9 times, so that'll be 34 times 9, minus negative 1 times 80, minus 3 times negative 26 times 9, minus 2 times 80, plus 1 times negative 26 times negative 1, minus 2 times 34. Phew. Let's stop and look over our work. Let me dot my I's and cross my T's here. That's a 9. All right. So that's going to be 34 times 9 is 306. Then it's minus negative 1 times 80, so it's going to be plus 1 times 80, or just 80. And then that's minus 3 times. Now 26 times 9, so that's going to be negative 234 minus 2 times 80 is going to be 160. Negative 26 times negative 1 will be positive 26. Minus 2 times 34. 2 times 34 will be 68. Now we are marching ever closer. Negative 234 minus 160 is going to be negative 394 plus, now 26 minus 68 is going to be negative 42. So now 9 times 386, it's going to be 3,474 minus 3 times negative 394 will actually become plus 3 times 394, so plus 1182, and then minus 42 essentially. And ultimately, you're going to have 4,614. Now, let me double check that. Yep, 4614. So that'll be our dy determinant. So yes, very calculation intense. It's kind of fun to have to keep up with everything, and it's a good management problem. Now, to get dz, that's going to be our last matrix we're going to have to find. We're going to take this third column and replace it with this. So we got that. We're going to move that into the third column. Duh. And then the second column is going to be the original second column. So we look at -1. I'm looking here, -1, 9, and 2. I'm going to use a nice shade of purple here. And we'll see once all these determinants fall, it's really not so bad after that. The calculations, the determinants are definitely the hardest part. So I'm going to again expand along this first column. 9, and then what I have left over is 9, 34, 2, and 80. Minus, now I hit the 3. Plus 1 times the determinant, -1, -26, 9, and 34. And now I'm going to have 9 times 80 minus 2 times 34 minus 3 times -1 times 80 minus -26 times 2 plus 1 times -1 times -34 minus -26 times 9 bada bing, bada boom. 9 times 80 will be 720. 2 times 34 will again be 68. +34 234. And we just work our way through it. Plus, and now, oops, 34 plus 234 should be 268. So of course I could never have gotten this done all on one screen here. That would have been ridiculous. Plus 84 plus 268. Everything's coming up positive. 6220. So as you can see, these are very calculation intense. We did work some 3x3 determinants last time that were not so nasty. The numbers were not so nasty. It appears I made a mistake somewhere. Let me double check my work here. It appears I made a very slight mistake. So as you can see, it's very easy to make a mistake. Well, 268. Okay. Let's see here. Where did I make an error? And if y'all spot one, then of course, please let me know. 9 times 80 minus 2 times 81 minus 3 times negative 1 times 80 minus negative 26 times 2 plus 1 times negative 1 times, made a very slight error. This was positive 34. I don't know why I put negative 34. So it just changes things very slightly. I think I already did the multiplication in my head. So this becomes just 200. There we go. So mistakes are always in the realm of possibility. 6152, and now that's the correct answer. Pardon. So now we have our DZ, 6,152. All right, we're finally ready to put this thing to bed. We'll clear off all this mess. We've done all the heavy lifting, all the hard parts. Now all we have, our solutions. Finally, we can breathe a great sigh of relief. Our solutions to our system of equations, x is going to be the dx determinant divided by the d determinant. So that's going to be negative 3,076 divided by 769, which will be a negative number. And now, yes, I'm using a calculator. It'll be negative 4. So the numbers are now finally going to start coming out pretty easy. They're going to be pretty straightforward. Our y value, this is the solution set, is going to be dy divided by d. So it's going to be 4614 divided by 769. And that's going to give you 6, a nice clean positive 6. And then the z solution is going to be our dz determinant divided by d, 6152 divided by 769. That's going to give you a nice clean 8. So even though all the determinant work was very complicated, we ended up getting our solution set as an x value of negative 4, a y value of 6, a z value of 8. And that's the solution to this 3x3 system. We can express this solution as an ordered triple, the x value, then the y value, then the z value. Whoo! Very good, very good. So we got that one in the bank. Again, I'm promising you, if you are to see something involving Cramer's rule on the final exam, the numbers are going to be much, much gentler. But it was good that we worked a problem like this together. On your homework, you're allowed to use a calculator, sure. Especially if you can tell the numbers are going to get nasty, you can pop a calculator open real quick. But really, the calculator didn't do any of the actual theory for us or any of the conceptual work for us. We still had to know how to set up the determinants, what they needed to be, and we even did most of the heavy lifting for the determinants. We just let the calculator do little grunt work, like 9 times 260 or whatever, stuff like that. So really not one that if the numbers were simpler, you wouldn't need a calculator for. Okay. So that was Crémare's rule in a 3x3 system. You got a nice taste of that. I think that's a good thing. You can earn your stripes on that a little bit. Now, what we're going to want to look at are going to be systems of inequalities. So this will be the next section, and this should be the final section we'll cover in this course. Systems of inequalities. I think I'll even give you a section number. So we already have a basic idea of what like a one variable inequality is. And this is something you should walk into this course already knowing something like this. All x values greater than or equal to 3. This is just a single variable x. We want all x values greater than or equal to 3, so that would be 3, 4, 5, 6, 7, 8, 9, 10. But even real numbers, so it can be 3.5, it can be pi, is certainly greater than or equal to 3. You can graph a one variable inequality if you so desire. Here is 0. I always like to put it in the center if it makes sense to. Here's 3. Everything greater than or equal to 3 means that if you use bracket notation, you use this bracket, and then you shade everything to the right. And when you're shading, you want to make your shading very clear what it is that you're doing. Of course, it goes off onto the arrow here, so it's actually saying it's shading all the way on to positive infinity. You keep going and going. You want to use real thick shading so that it's clear what you're doing. I would not use real slim shading. You want to use real thick shading so you can see it all. So that is graphing an inequality, but that's just in one variable. In this case, it was x. Well, one variable is just not all that interesting. It's not the most interesting thing in the world, not the most interesting thing we can do. Instead, we might be a lot more interested in doing two variables. Something involving both x and y. So let's try graphing x plus 2y less than or equal to 8. X plus 2y less than or equal to 8. Suddenly we have a linear equation here. Almost. It's an inequality still, But when we graph this thing, we're going to be best off to think about it as a linear equation. So let's look at a graph. The standard XY plane. To graph this, we're going to go back in time to when we were youngins, when we were children, running around, watching. Boy, I don't know what your generation would have watched. Probably iCarly or Wizards of Waverly Place. I think that sounds about right. You guys are about 17, so maybe something like that. Anyways, we're going to go back in time. We're going to play pretend. We're going to pretend that we have an equation. We're going to pretend that we have the equation x plus 2y equals 8. We're going to graph this equation first. And then what we're going to do is we're going to shade. That's going to create a line. You can tell that's a linear equation. We're going to shade either entirely above the line or entirely below the line. And we're going to use some special trickery to figure that out. So here, if you want to, and this is kind of just a side, we have already looked at graphing linear equations, but we can graph by intercepts. We can find the x-intercept, and we can find the y-intercept. Remember, the x-intercept is found by basically assuming that the y value is 0. So you're just going to have x equals 8. Your y-intercept is found by assuming a 0 for x. If you remember our strategy, so that's going to be an x-intercept of 8, 0. So I'm going to graph that. And a y-intercept of 0, 4. So my line is going to look something like that. And I'll label these points. Eight, 0. This point is going to be 0, 4. Just graphing by intercepts. So whenever you're graphing these, you always start out assuming that you just have an equation, like you're just graphing a line. But then we need to do a few extra steps. Then, if you have a strict inequality, that is, if you're using a strict less than sign or a strict greater than sign, use a dashed line. So if we had that, which we don't, but just to play pretend, if we had that, we would need to make this a dashed line. There might be a better way. Let's see. We would say, oh, look at that, it's dashed, and you can go on and imagine it, blah, blah, blah. However, that's not the case. That's not what we have here. Otherwise, use a solid line. So I'm going to have to use some undos here. We have the other case. We have a less than or equal to. So we're going to use a solid line. The cool thing is that whenever you're graphing these things on your online homework, and if you were to have to graph them on the final exam, if this was one of the potential problems on the final, there's a very simple tool you'll find whenever you graph a line that even after you've graphed it, you can go in, and as long as you have the line selected, you can go in and tell it to be a solid line or a dashed line. It's a little drop-down menu. It's very straightforward. You'll see it. So we've graphed the line. We've decided that it should be a solid line. Finally, we have to deal with the shading. We are going to end up graphing either the entire, and after I sneeze, I'll tell you. Excuse me. Excusez-moi. After we've graphed the line, decided whether it should be dashed or solid, we're going to end up shading the entire region either below the line or above the line. So what you're going to do is you're going to pick a test point that's not on the line. So you can pick any point on the graph as long as it's not on the line. You can tell from how it is, from how the graph looks, that if I were to pick the origin, which is almost always a good test point to use unless the line crosses through it. You can't use a test point that's on the line itself. But as you can see, the origin, which is the point 0, 0, oops, is not on the line at all. We're going to use the test point. You're going to plug the test point into the inequality. If you end up with a true statement, shade the region with the test point. If you end up with a false statement, shade the other region. So it's a really simple test. We're going to literally take 0, 0, we're going to plug it in for x and y, and if we created a true statement out of that inequality, we're going to shade the region that that test point is in. Otherwise, we're going to have to shade the other region. So we're going to take 0, 0, testing 0, 0. I'm literally going to put a 0 in for x, a 0 in for y, and now I'm asking, is this less than or equal to 8? That's going to end up 0 less than or equal to 8. And I have a true statement here. 0 is indeed less than or equal to 8. True. So I'm going to shade this entire region that the point 0, 0 is found in. Now on your homework, you're not going to have to do this really, really lame way of shading that I'm going to have to do here. I mean, I literally just have to go like this and say, ooh, I'm shading everything in this case below the line. That includes all this. And unfortunately, my tools are limited here. It's going to look like hogwash. And I mean, it literally shades even off the graph theoretically. It's everything below it. And the graph has to stop at some point. But the shading is an infinitely large area. But that looks bad. What you're going to have, you guys are going to have the privilege of your online homework just has a little paint bucket tool. So just like there's a little tool that you can choose between a solid line and a dashed line, you're going to have a paint bucket tool on your homework. What you do is after you've graphed the line, after you've decided if the line should be solid or dashed, then when it's time to shade the appropriate region, you're going to go grab your paint bucket tool and you're going to just click the region you want. You would literally click this region here and it's automatically going to shade it. And I believe it uses the yellow. It uses yellow. And that's how we're going to graph a linear inequality. It's just graphing the line with a little bit extra. You got to shade above or below the line. Now, we actually have a lot of work to do then if we want to have a system of inequalities. Because a system of inequalities, this was just a single inequality here that we just graphed. A system of inequalities is going to have multiple. It's going to have multiple inequalities. If you think about the word system, it makes sense. So let's try this one on for size. X plus y greater than 0. Two x minus y greater than or equal to 1. We're going to graph this system. We're going to graph them all on the same exact XY coordinate plane. So I've got my XY coordinate plane will look something like this. So let's just do it piece by piece. Let's look at x plus y greater than 0. And you know what? Let's color coordinate. Let's do that. Let's use Christmas colors because it is that time. We're going to let this one be the green one, this one be the red one, and now you'll see what I'm going to do here. Imagine you were graphing the line x plus y equals 0. You could solve that and it would be y equals negative x if you move the x over. So we're not going to use intercepts on this one. It wouldn't help us. This would be a line with slope -1 and the y-intercept would be 0, 0. As you can see, if you remember your y equals mx plus b form, b would be clearly 0. The slope is -1. So the line is going to be basically that. Crosses through the origin, so suddenly we may not be able to use the origin as a test point, but that's okay. Now we have to ask, should it be shaded? Excuse me, I'm sorry, should it be dashed or solid? Well, wait, look back at the original line itself, which is this guy. The inequality is a strict greater than. So it should actually be dashed. Because if it's a strict greater than, there's not the or equal to on it. It's like saying we can't actually be on the line itself. That's just going to be a boundary. So we have to make it a dashed line. Again, your online homework has a very simple way of making dashed lines for you. Your grapher tool on your online homework is really convenient, to be honest. And we'll make it nice and dashed. It'll look very pretty. And that's not so bad. Now, finally, should we be shading above the line or below the line? Should we shade above the line or below the line? Well, we're going to use a test point. Unfortunately, we can't use the origin as a test point. That would be just too gosh darn convenient. But unfortunately, this line actually does pass through the origin because it had a y-intercept of 0, 0. So, okay, darn. That's all right. What we're going to do is you're going to pick a test point. Where's my thing? Here we go. Let's try a test point. Well, I would wager that, okay, 1, 1, that point there, that's not on the line, which is perfect. So that's going to be my test point that I'm going to try out. And I'm going to try it out in this first inequality here. So I'm going to plug a 1 in for x plus a 1 in for y. And I'm asking if it's a true statement greater than 0. Is 2 greater than 0? Yes. So what we're going to do is we're going to end up shading this region here. I'm not going to fully shade it just yet because we would shade all that in green. But now we also have to deal with this second line here. So back to the drawing board. I'm going to use red for it. And there's a couple things we can do. We could use intercepts, you know, just depends on your fancy, or we can graph it using y equals mx plus b form. Let's try it that way. So I'm going to move the 2x over to the other side. And then since it's negative y, I'm going to multiply both sides by -1 because we want to get the y by itself. And that's going to flip the signs on everything. So now this is a line with slope 2, y-intercept of 0, -1. The slope is 2, the y-intercept -1 is the key part here. So we're going to come down here to 0, -1, and then we're going to have a line with a slope of 2. Real quick, I'm going to erase this old test point because it doesn't matter anymore. So it's going to cross through 0, -1 and have a slope of 2. So it's going to be pretty steep. Bada bing, bada boom. Put some arrows on it. So we've got the line graph. Very good. Our next determination, should it be solid, dashed? Well, in this case, the inequality was greater than or equal to. It has the or equal to element, thus it should be solid. So I don't have to worry about dashing it or anything. I don't have to worry about dashing it. So that's in the bag. Finally, where should I shade? Well, now we couldn't use 0, 0 as a test point for the green line, but now if you'll notice, 0, 0 is not on the red line. So we can use 0, 0 as a test point for that. So use 0, 0 as a test point. We're plugging it into the second inequality. There'll be 2 times 0 minus 0 greater than or equal to 1. We're trying to figure out whether this is true. Well, 2 times 0 is 0. It's just going to end up being 0 on the left-hand side once you subtract off 0. And then we're asking, is 0 greater than or equal to 1? No, that's a false statement. So here's where that test point was. So we don't shade this region, we shade the opposite region, everything below the red line. But here's the final part. Now our solution region is going to be everything that is double shaded. That is everything that has been shaded by all the inequalities in the system. Because when you're saying graph this system, you're saying x plus y greater than 0 and 2x minus y greater than or equal to 1. You want both inequalities in the system to be satisfied. If you just look at this region here, this little triangular looking region, it's only shaded red. It's not also shaded green. Thus, only the second inequality is satisfied in this region. If you look at this little triangle-ish shaped region over here on the left, it's shaded neither red nor green, so neither inequality is satisfied. If you look at this region, it's only shaded green, so neither inequality is satisfied. But finally, if you look at this little region here, it's been doubly shaded, thus it is valid for both the green shading and the red shading, and thus it's valid for both inequalities in the system. So the true region of shading is going to be this, and we'll use blue here. It's going to be this region here, comes down to this line, but doesn't quite touch it because it's dashed. Again, you're going to use the paint bucket and select this little region. Now, everything on the red line up here is actually a solution, but there you go. And so, yes, that looks terrible, but that's life. So this is how we graph a system of linear inequalities. We're basically just graphing each linear inequality and looking at it one by one, because that's all we really can do at the end of the day. Finally, let's recall horizontal and vertical lines. Horizontal and vertical lines. Remember, if you had the line x equals 3, and this was supposed to be a line in the xy coordinate plane, whenever it's an x equals equation, it's going to make a vertical line. It's going to be the vertical line that passes through the point 3, 0. So something like this, a straight up and down vertical line. And so that's how you would graph x equals 3. But now let's play around with some of the possibilities of turning it into an inequality. Instead of x equals 3, let's say you had x greater than or equal to 3. Well, just like earlier, you have to start by graphing the line itself, which we have here. Then you have to decide, should that line be solid or dashed? Well, it's greater than or equal to, so it should be solid. Now, the nice thing is you don't even need to pick a test point. There's no need for a test point, because if it's greater than or equal to 3, you're going to, if it's a greater than, you're going to shade everything to the right of it. Like that. If it were less than or equal to 3, you would just shade everything to the left of it. So that's a really cool little factoid. If it was supposed to just be x less than 3, you would have to deal with a dashed line. But the shading would remain the same in that case. So being less than a vertical line means being left of it. Being greater than a vertical line means being to the right of it. And yada, yada, yada. Real quick, horizontal lines. That's going to be y equals some constant, some number. So for instance, y equals -2. It's going to be a horizontal line. It's going to pass through the point 0, -2 and be horizontal. Like that. As for shading, if you have less than or equal to, you shade below. So the less than for a horizontal line means to shade below. Kind of makes sense logically. You could prove it using a test point. It would still work. If you had to shade above, it would be a greater than or equal to, or a greater than. And then you would just know to make it dashed if it was a strict inequality. And that looks like that's it for today. So we'll meet on Thursday and do a review session during this time.
You guys listen? Hey, you just said you're getting a review session on Thursday.
Have a good day. We'll see y'all on Thursday.
All right. Thanks. Everybody was